In the last video, we discussed exponential functions and how you differentiate them. So specifically, the exponential function e to the power of x is special because it's its own derivative. So anytime we differentiate e to the power of x, we get e to the power of x. It's its own derivative. So closely related to exponential functions are logarithmic functions. So in this video, we're going to talk about how you differentiate a logarithmic function. So first off, what is a logarithm? So a logarithm is defined as the inverse or opposite of its related exponential. So they are related to exponentials by the inverse relationship. So what does that mean? Well, addition and subtraction are inverses. An exponent and a radical are inverses. An exponential and a logarithm are inverses. So suppose we want to solve this equation for x. 10 to the x power is equal to 1,000. Well, more than likely, you can probably determine in your head what the exponent would have to be to make that true. So the number that solves this equation is the number 3, 10 to the third power is 1,000, but the name for this number, for the number that solves an equation of this form, is a logarithm. So specifically, this is the logarithm. It represents the logarithm base 10 of the number 1,000. So what does that mean? Well, it means a logarithm represents an exponent. So a logarithm is another name for the exponent that makes an equation of this form true. So when the variable you're attempting to solve for is in an exponent rather than being the base, normally we see the base as being variable and then the exponent is a fixed number. Something like x squared is equal to 1,000. We're solving in a different way. But if we allow the base to be a fixed number and then the exponent is variable, then when we solve for that exponent, it's referred to as a logarithm base 10, so based on the base of this exponential, of the number that we're trying to equate to. So what is the actual inverse relationship? And I'll try to help you figure out what this logarithm thing actually means, because this is mysterious to a lot of students. What is a logarithm? So here is the inverse relationship. So suppose we have this statement that y is equal to b to the x power. So x is our input, y is our output, b is a fixed base. It's a constant number. The equivalent statement is that x is equal to the log base b, so that's a subscript, of the number y. So you have to be very careful when you write an expression of this form. This is what we call the base of the logarithm. It's a subscript. So if log is written on the line, b is written below the line. And then the number that we're applying this function to, this is a function, the number we're applying it to is also on the line. So when we see something like this is a logarithm. We read that as the logarithm base b of y. Here's how to think of what that means. Think of it as asking a question. This is the question it's asking. It's asking the base, in this case b, to what power? The base to what power is y. That's what that is asking us to find. So the exponential statement tells us if we take our base and raise it to this power, we get out y. Well, when we see something like this is asking us essentially to answer the question that we answered over here. It's asking us the base, b, raised to what power would give us this value, y. Well, based on this statement, we know the exponent we would need to make that true would be the exponent x. So when we evaluate this logarithmic expression, x is going to be the answer. It's going to be the value that this logarithm evaluates to. And once we put some numbers in there, it'll probably make a little bit more sense. But the biggest thing to remember is anytime we see something logarithmic, it also corresponds to something exponential. We're used to working with exponents even if we're not used to working with logarithms. So if the logarithm concept is ever mysterious, we can always convert it to something exponential, and that'll help us make a little bit more sense of what we're looking at. So how do we convert? Well, here's sort of a shortcut for converting. The biggest thing to remember is that the base of the exponential, which is the big number, if we're talking about an exponential, that's the fixed number, and then we know the variable is in the exponent. The base of the exponential is also the base of the logarithm, which is going to be our subscript. And then the other two numbers in the problem, x and y, or whatever they happen to be, if they're actual fixed numbers, they're going to switch places. They're going to swap places across the equal sign. So let's just practice doing some conversions to take a logarithmic expression and convert it to something exponential. So our first equation, this is a true statement, log base 3 of 81 is equal to 4. Now it's worth mentioning, notice I don't have parentheses here and yet I put parentheses here. It's considered acceptable with a logarithm if you're only taking the logarithm of one value to leave off the parentheses. So this is equivalent to log base 3 of 81 in parentheses. These two statements are equivalent to one another. Just for sake of saving a little bit of time, a little bit of writing, it's acceptable to write a logarithm in this way. But if we're ever confused about the structure, what is what is not inside of our function, it's always a good idea to write it with parentheses if needed. So the log base 3 of 81 is equal to 4. So what if I just saw this, the log base 3 of 81? What is this saying? It's asking the question, 3 to what power is equal to 81? Well, 3 to the 4th power is equal to 81. So the log base 3 of 81 is equal to 4. Now, how would we write that statement in an exponential form, though? Well, number one, the base of the logarithm becomes the base of the exponential. So the base in the logarithm is going to be the subscript. When we convert to an exponential, that subscript is going to become the big number. Now I'm going to go ahead and put in my equal sign. So once I take care of the base, the other two numbers in my problem are going to switch places. So 81 is going to go over here. And then I have to think about what I have and what I'm missing. So I'm attempting to write something exponential, which means a base to a power. So I have my base. What I'm missing is my exponent. So when 4 moves over to be on the same side as the 3, 3 is our base, which means 4 has to become the exponent. Notice what we end up with is a true statement. When we convert a true statement, we end up with another true statement. So log base 3 of 81, 3 to what power is equal to 81? Well, 3 to the 4th power is equal to 81. That is the same thing as saying 3 to the 4th power is equal to 81. So this would be the conversion in exponential form. So essentially this equation and this equation are saying the same thing, they're just saying it in a slightly different way. Okay, next one. Log base 8 of 2 is equal to 1/3. So if we were to think of this as a question, it's asking the question 8 to what power is equal to 2? Well, how do we take something and apply an exponent and get a smaller power? Well, that means we have to have a fractional exponent. Another way to think of it is if we were to take the cube root of 8, we would get a 2. Well, the exponential equivalent of a cube root is an exponent of 1/3. So 8 to what power would give us 2? Well, 8 to the 1/3 power would give us 2. Now, what if we want to convert this, put this in exponential form? Now remember, the base of the logarithm, in this case 8, becomes the base of our exponential, the big number. Put in your equal sign. The other two numbers are going to switch places across that equal sign. So 2 is going to go over to the other side. And then this is going to move over with the 8. Well, if 8 is the base, we're missing the exponent. So the exponent is going to be 1/3. 8 to the 1/3 power is equal to 2. Well, let's verify that that's a true statement. What is 8 to the 1/3 power? Well, you can type it into your calculator. 8 to the 1/3 power is 2. So as long as we convert it and end up with something true, that's a pretty good indication that our conversion is correct. Now, keep in mind, we don't have to have actual fixed numbers in place to make sense of what a logarithm is, as long as we go back to this idea of the question that it's asking. So in this case, we're saying log base A of C is equal to D. In other words, we're asking the question, A to what power gives me the value C? Well, whatever A and C are, they're related in such a way that A to the D power is going to give us the value C. So how would we convert this to exponential form? Well, the base of the logarithm in this case is the base A, it's some unknown base. We're saying A to what power gives me an output of C? Well, A to the D power gives me an output of C. So that would be our conversion. So if we then embed variables into these equations, we can solve for variables in the context of a logarithmic expression. And we can solve, depending on where the variable is, in lots of different ways. So let's look at a few examples where we need to find an unknown. And when in doubt, fall back on this definition for what a logarithm is, or go back to this idea that we can convert to something exponential. So the log base 3 of 9 is equal to x. We want to know what is x. In other words, what is the log base 3 of 9? Well, again, think of this as asking a question. It's asking the question, 3, our base, to what power gives us 9? What power would we have to raise 3 to in order to get an output of 9? Whatever that value is, that's our value for x. So x is equal to what? Well, if we're not sure, rewrite this in exponential form. So the base of the logarithm becomes the base of the exponent, okay? And then we want to be equal to 9. And so x, our unknown, is the exponent that relates those two values. So 3 to what power gives me 9? Well, 3 to the second power gives me 9. So x is equal to 2. So the log base 3 of 9, 3 to what power gives me 9? Well, 3 to the second power gives me 9. So x is equal to 2. Now what if x moves so that it is now the base of our logarithm? So now we're saying something to the second power gives me 25. So our base to some power gives us 25. Well, in this case, our base to the second power gives us 25. So what would x have to be? Well, you might be thinking there's actually two answers here. And the answer is kind of yes, kind of not. Technically, the answer is only 5. So this particular equation would be solved by both a 5 and a negative 5. But when we defined an exponential, when we defined this idea of an exponential, we defined it in such a way that the base has to be greater than 0. Well, that also means that this base has to be greater than 0. So since the variable we're solving for is in the base of this logarithm, it can't be a negative number. So the only value that would make this equation true, and thus this equation true, is going to be the value 5. So the only other place we might encounter that variable would be as the input for the logarithm. So think of log base 16 as the function. It's being applied to an input of x. So what is this saying? This is saying 16 to some power gives me x. Well, 16 to the 1/2 power gives me x. So let's rewrite this in exponential form. So the base of the logarithm becomes the base of the exponential. The other two numbers switch places. So x moves over here, and 16 is the base, so 1/2 is the exponent. So 16 to the 1/2 power. Well, what does a 1/2 power mean? Well, remember, that's the same thing as a square root. So we're saying x is equal to the square root of 16, and we know the square root of 16 is going to be 4. So in that case, x is equal to 4. Okay, so now that we have a sense of what a logarithm is, most importantly, what kind of question it's asking, always fall back on that idea of it asking a question and the fact that it can be converted to something exponential. Now that we have a general sense of what a logarithm is, let's talk about some special properties of logarithms that are going to help us simplify different expressions involving logarithms. So when we take the logarithm of a product, so the log base b, of something that has been multiplied together, another way of writing that is the log base b of just the first part of the product plus a separate log base b of the second part of the product. So essentially what this rule says is that if we have a product inside of a logarithm, we can split that up into two separate logarithms that are added together. So multiplication on the inside of a logarithm becomes the addition of two separate logarithms. Now we have a similar rule with division, with a quotient. So what if we have division inside of a logarithm? Well, that is also going to break apart into two separate logarithms, but it's going to be two separate logarithms separated by subtraction. So the logarithm of a quotient is equivalent to the difference of two individual logarithms. And notice it's going to be the logarithm of the numerator minus the logarithm of the denominator. Now the next rule is a rule involving exponents. So what if we apply a logarithm to something involving an exponent? Well, this rule says essentially we can bring the exponent out and it becomes a coefficient for our logarithm. So if we apply a logarithm to an input containing an exponent, notice the exponent is inside of the logarithm. That's going to be important that it is inside the logarithm. If there is an exponent inside the logarithm, we can bring it down and then it becomes a coefficient multiplied by our logarithm. Now the inverse rule, this is essentially going to tell us how an exponential and a logarithm negate one another. So if we multiply and then divide by the same number, essentially the idea is that everything cancels out. If we add and subtract the same number, everything cancels out. The same kind of thing happens when we apply both a logarithm and an exponential. So if we apply a logarithm of a particular base to an exponential that also has the same base, notice the base has to be the same. So log base b, exponential base b, essentially the idea is that they cancel one another out and we're just left with whatever would be in the exponent. In this case we're calling that k. And then also, last but not least, the logarithm base b of 1. What is that? The logarithm base b of 1. So we're saying b to some power is equal to 1. Well, b can be anything we want as long as it's defined for the logarithm, so just something greater than 0. So we're saying some number greater than 0 raised to a power gives us an output of 1. Well, the only exponent we have that we could raise anything to and get an output of 1 is going to be 0. So the log base b of 1, regardless of what the base is going to be 0, identically equal to 0. So let's look at a few examples using these rules. So just to recap, multiplication on the inside of a logarithm can be split up into the addition of two separate logarithms. Division on the inside of a logarithm can split up into the difference of two logarithms. An exponent inside of a logarithm can be pulled out front. It becomes a coefficient. A logarithm and an exponential of the same base cancel each other out, essentially just leave us with the exponent. And then a log of 1 is always going to be 0. And of course we can flip back over if we need these. So let's look at a few examples. Now, it's important to preface that we're kind of limited as to what we can do with logarithms in the calculator. So if you look at your calculator right now, Over next to the 7, to the left of 7, you see log. That means something specific. That means a log with a base of 10. Now the number below that, the 4, and then the button to the left of that, it says ln. We'll talk about that in just a minute. But essentially, you don't have a general way to plug logarithms into your calculator. You can plug in any type of exponent you want to your calculator, but your calculator can't necessarily handle logarithms in general. So using these kinds of rules is going to be helpful in allowing us to simplify things that we can't otherwise just plug into the calculator. So just be advised, the calculator is not going to be able to do all of the work for you when it comes to something like a logarithm. So here we've been given some information about a couple of different logarithms. We've been told that the logarithm base a of 2, notice we don't know what the base is, we've just been told that it's the base a. The logarithm base a of the number 2 is 0.301, and the logarithm base a of the number 3 is 0.477. So based on this given information, we want to find each of the following. So first thing we want to find is the log base a of 6. So what's the goal here? The goal is to find an actual numeric value for each of these expressions, but only using what we already know about these two logarithms. Because if we don't know what the base is, there's no way we could type something like this into a calculator. We'd need a fixed base, we need an input, we have the input, we don't have the base. But as long as we have information about logarithms related to this one, then we can potentially use those logarithm rules combined with the information we have here to evaluate our other logarithms. So we've been told that the log base a of 6 is what we want to find. Well, how does that relate to these two logarithms? Well, when I look at these two logarithms and I compare to an input of 6, I notice I'm looking at an input of 2 and an input of 3. So if I were to take a 2 and a 3 and multiply them together, I know that gives me a 6. So another way to write this logarithm would be log base a of 2 times 3. So 6 is going to be the same thing as 2 times 3. Well, what's the benefit of doing that? The benefit of doing that is now I have a product inside of my logarithm, and I have a logarithm rule that says when there's multiplication on the inside of the logarithm, we can split it up into two separate logarithms that are added together. So this is going to be the same thing as log base a of 2 plus log base a of 3. These two have given values. So now I can just sub in the values I was given. So that's going to be 0.301 plus 0.477. And I can simplify that in the calculator. So 0.301 plus 0.477. And that's going to give me 0.778. So that is going to be the value of my logarithm based on the logarithms I was given. Now what about the next one? We have logarithm base a of 2 divided by 3. Well, this one in some ways is easier than the previous one because we already have a quotient inside of our logarithm. 2/3 is the input for this logarithm. So the quotient rule tells us that we can take this logarithm of this quotient and split it up into two separate logarithms that are subtracted. So the logarithm base a of our numerator minus the logarithm base a of our denominator. And then again, these two are values I've been given. So that's going to be 0.301 minus 0.477. And again, I can go to the calculator. So 0.301 minus 0.477. That's going to give me negative 0.176. Okay, let's look at the next one. We may have to be a little bit more creative here. So we want the log base a of 81. Now I can't necessarily think of a way to combine 2 and 3 and generate 81. If we take 2 and multiply it by 3, we get 6. Okay, if we multiply by another 3, then we get 18. If we multiply by anything related to 2, we're going to get an even number. So log base A of 2 can't be multiplied here in order to generate an 81. So automatically that tells me the only way I can get to an 81 is maybe involving this. There's another way to get to this input though. Rather than thinking of it as relating to 2 and 3, maybe think of it in terms of an exponent. So we know anything related to 2 is going to give me an even value. So I'm not going to be able to use 2 to generate 81. But 3 raised to a certain power actually does give me 81. As it turns out, 3 raised to the 4th power would give us 81. So another way to write this logarithm would be log base A of 3 to the 4th power. And again, the benefit here is that now we have a logarithm rule that applies to this expression. As soon as we have an exponent inside of a logarithm, we have a rule that says we can now bring that exponent out and it becomes a coefficient. So that becomes 4 times log base A of 3. This is something we have a value for. So now I can sub in my value based on what I was given. So that's going to be 4 times 0.477. So 4 times 0.477, and that's going to give me 1.908. Okay, let's try another one. So log base A of 1/3. So this one looks pretty similar to this one. Okay, so we can use that quotient rule. So let's see what happens if we split this up. So that's going to be log base A of 1 minus log base A of 3. Well, log base A of 3, we have a value for that. But what about log base A of 1? It doesn't look like we've been given that value. But wait, remember, flip back over. The very last property we have, the logarithm any base applied to an input of 1 is identically equal to 0. So the log base A of 1, based on that rule, is going to be 0. So that's going to be 0 minus our log base A of 3, which is going to be 0.477. And so we simplify all that, and that's going to be negative 0.477. Okay, what about the next one? Log base A of the square root of A. Well, I don't see anything related to base A and an input of A. So more than likely these two are not going to help us here, which means we're going to have to fall back on those rules. Now, from all of that taking derivative expertise we now have, we know that square roots can be written in a different way. They can be written with an exponent. Well, if I can write something like this with an exponent, then I can maybe use a rule kind of like this. So what does a square root look like as an exponent? Remember, a square root is the same thing as an exponent of 1/2. So this is going to be the same thing as log base A of A to the 1/2. We also have a rule that applies to an expression like this. So we know that anytime we take a logarithm of a particular base and apply it to an exponential of the same base, the bases have to match, those expressions are inverses. They eliminate one another, and all we're left with is our exponent. So in this case, we have a logarithm base A and an exponential with a base of A. So the logarithm, the exponential base, those are inverses, and they're going to cancel, and they're just going to leave us with the 1/2. Okay, and then one more. So log base A of 2 times A. So I look at this and I see a product. Okay, I know I have information about the log base A of 2. What about log base A of A? Well, we'll look at that in just a minute. So log base A of 2, and then since we're looking at a product, it's going to be 2 logarithms that are added together. So log base A of A. So log base A of 2, we have a value for that. So that's going to be 0.301. Now what about log base A of A? Well, it's actually very similar to this situation right here. The only difference is that we don't see an exponent written. But if we don't see an exponent written, we know there's an implied exponent of 1. So if we wanted to write this logarithm's input with an exponent, it's an implied exponent of 1. And now we can essentially use the same rule. So we now have a to the first power inside of this logarithm, and we know that a logarithm with a particular base and an exponential with a matching base are inverses. They cancel, so they're just going to leave us with the 1. So log base A of A is identically equal to 1. And so if I add those together, I'm going to get 1.301. So as you can see, using these logarithm rules allows us to take situations where maybe it doesn't look like we have a lot of options and open up the doors to some additional options. So now let's talk about a specific logarithm with a specific base. So we have a natural exponential function. We also have what we refer to as a natural logarithm. So a natural logarithm is the logarithm with a base of e. So we talked about that number e in the last video when we talked about exponentials. Remember, e was special because when we look at e to the x power, we take its derivative and we get the same function back out. It's its own derivative. E is also encountered in a lot of applications in the real world. So if we encounter e, we're also going to encounter the logarithm that has a base of e. Now when we write it, if we want to write the natural logarithm function, if we were going to use the notation we normally have, that's going to be log with a base of e applied to our input of x, but we're actually going to abbreviate this. So in place of log base e of x, we're actually just going to write ln of x. So ln is going to be our abbreviation for natural logarithm. And if you look on your calculator, right under the log button, next to the 4, it says ln. That's going to be the button you use to evaluate something related to this logarithm. All of the rules we just looked at that apply to logarithms are going to apply to this particular logarithm as well. It's just a logarithm with a specific base. In this case, the base is e. All of those rules are still going to apply. So let's do a few examples simplifying things involving our natural logarithm. And these, fortunately, we can check in the calculator. So we're going to take the same approach just so we can get some practice with those logarithm rules. If we have information about two different logarithms, how can we use that to generate information about an unknown logarithm? So we've been given a value for the natural logarithm of 2 and also the natural logarithm of 3. And we want to find each of the following values. So what about the natural logarithm of 6? Well, we know from the previous example that we could take 6 and write it as the product of 2 and 3. And if we have a product inside of a logarithm, we know we can split it up into two separate logarithms that are then separated by addition. So natural log of 2, based on what we've been told, is 0.6931. This is actually just an approximation of it. And then natural log of 3 is 1.0986. And so if we simplify all of that down, 0.6931 plus 1.0986. And that's going to be 1.7917. Now what happens if we evaluate natural log of 6 in the calculator? So if you want to do this, you're going to press the natural log button first, and then you'll type in your input. And sure enough, we get a number that's roughly that value. Now what about the natural log of 81? We also looked at an example similar to this. Remember, we couldn't generate an 81 from both a 2 and a 3. Anytime we multiply something by 2, we generate an even number. This one's odd, so that's not going to help. But we recognize that we could take 3 and raise it to the 4th power, and that's another way to write 81. Using that approach allows us to use that exponent rule that tells us that we can bring down an exponent that's inside of a logarithm, make it a coefficient, and then just multiply by the logarithm with no exponent. Now we know the natural log of 3, so that's going to help us here. So the natural log of 3, approximately 1.0986. So we simplify that down, 4 times 1.0986, and that's going to be approximately 4.3944. And let's check that in the calculator. So natural log of 81, and sure enough, we get something close to that. Okay, what about natural log of 1/3? Well, again, now we have a quotient inside of our logarithm, and we know we can split that up into the logarithm of the numerator minus the logarithm of the denominator. Now, what is the natural log of 1? Don't look at this and get concerned. Remember, this is really just the same thing as log base e of 1. And we know when we take the logarithm of any base applied to an input of 1, it's always going to be identically equal to 0. Let's verify that in the calculator. If we took the natural log of 1, there you go, we get a 0. So 0 minus the natural log of 3, which is 1.0986. And so 0 minus that value is just going to make that value negative. So 1.0986, just negative. Okay, one more example. So the natural log of 2 times e to the 5th power. So e to the 5th power, e is our natural exponential base, and now it's being raised to the 5th power. But keep in mind, e is a fixed number, so e to the 5th power is also a fixed number. It's a fixed number multiplied by 2. So we can essentially use the rule that we used in part A. We can split that up into the product of two separate, not the product, the sum of two separate logarithms. So 2, natural log of 2, plus natural log of e to the 5th power. Now, natural log of 2, that was one of the values we were given, so 0.6931. What about the natural log of e to the 5th power? Well, remember, natural log is really just the same thing as log base e. We don't write it that way, but that's really what it is. So we're in one of those situations where we have a logarithm with a particular base, and it's being applied to an exponential that happens to have the same base. We know the logarithm and the exponential are inverses. They eliminate one another. In this case, just leaving that exponent of 5. So the log base e, the natural log of e to the 5th power, is just going to be 5. So we add those two values together, 5.6931. And there we go. So before we look at the calculus component of this, differentiation, let's talk about one more situation where we may use a logarithm and how we can use it. So logarithms can also be used to solve equations that contain exponentials. So a logarithm essentially cancels out the exponential with the same base. And that's based on that inverse rule we saw. So anytime we take a logarithm with a particular base and apply it to an exponential that has the same base, the logarithm, the exponential, cancel one another out, and we're just left with whatever was in the exponent. So suppose our variable is in the exponent of an exponential expression. How do we solve for it? The goal is to get rid of the base of the expression and keep the exponent. So something like taking a square root or a cube root is not going to help. Anytime we take a square root, we eliminate the exponent and keep the base. Well, what if we want to get rid of the base and keep the exponent? Well, this is where we're going to use a logarithm. So suppose we know that e to the x power is equal to 80. We want to know what exponent would make that true. We want to solve for x. Well, if we want to get rid of the e, but keep that exponent, isolate that exponent, that's where we're going to use a logarithm. It has to be a logarithm of the same base, though. In order to cancel out something, it's got to have the same base. So if we want to get rid of a base of e, we're going to use a logarithm base e, what we also call the natural logarithm. So just like I could do something like applying a square root to both sides, I can also apply a logarithm to both sides of the equation. So I'm going to apply the logarithmic function base e, the natural log, to each side of the equation. I know that whatever I do to one side, I have to do to the other in order to keep everything in balance. Now, how does that help us? Well, the natural log of e to the x power, this is log base e, this is the exponential base e, and so they cancel one another out, and we're just left with x. So x is equal to the natural log of 80. Now, do we stop there? Is that the actual answer? It kind of depends. So if you're told to give the exact answer, this is the exact answer. Anytime we take e to a power or apply a natural logarithm, we typically end up with an irrational number. In all except a very small handful of cases, we end up with an irrational number. So plugging this into the calculator only gives us an approximation. So this is the exact answer, but suppose we were doing an applied problem and we wanted a more, I guess, useful answer. That's when we can plug it into the calculator and approximate. So the natural log of 80 is approximately, we'll just say 4.382. There we go. Okay, let's try another one. This one looks a little bit more complicated, but notice it's structured in basically the same way. So we have e to a power is equal to 0.05. So we want to get rid of our base so that the variable comes out of the exponent. So if I want to eliminate a base of e, and I want to use this rule, I'm going to use a logarithm base e, or the natural logarithm. So the natural log of e to the negative 0.04, and in this case we have the variable t, is going to be the same thing as the natural log of 0.05. So do it on both sides to keep things in balance. So on the left-hand side, log base e, natural log, exponential base e, those are inverses, they cancel out, and so we're just left with the exponent. Now notice there's a little bit more going on in the exponent here than there was before. We're left with the entire exponent, not just the variable. So that's going to be equal to the natural log of 0.05. So if I want to isolate my variable, in this case t, I'm going to divide out the coefficient on both sides. So we have the natural log of 0.05, which is just a number. It's not a pretty number, but it's just a number. And that is then being divided by negative 0.04. Now, as tempting as it is, you can't do anything to either cancel or somehow combine 0.05 and negative 0.04. 0.05 is inside of the logarithm. Think of it kind of like something that's under a square root. Something under a square root can't cancel out with something that's not under a square root. So 0.05 is locked inside of that logarithm. This particular thing that we're dividing by can't be combined with the 0.05. So this would be considered our exact answer. That's the simplest form we can write. And of course, if we want our approximation, we just plug that into the calculator. And you can plug that in one line. So natural log of 0.05, and then we're dividing by negative 0.04. And so to 3 decimal places, that's approximately 74.893. And there we go. Okay, so what have we done so far? We've defined a logarithm. We've worked on converting between logarithm and exponential form, just because the exponential form maybe makes a little more sense. It makes a logarithm a little clearer in terms of what it means. We've talked about some logarithm properties that allow us to simplify expressions containing logarithms. And then we've also introduced this idea of this natural logarithm, specifically the logarithm base e. So now let's get to the calculus portion. Let's talk about how you would take the derivative of a logarithmic function. So just like we focused only on a base e when we looked at exponentials, we can have a variety of bases. We just focused on base e because base e is special. We're also only going to look at what happens with a natural logarithm, with the logarithm base e. Keep in mind there are ways of taking a derivative for something with another base. They use slightly different rules, slightly more complicated rules than what we're looking at, but they're essentially variations of the rules that we're using here. So what is the derivative of the function f of x is equal to the natural log of x? So if we're taking the derivative with respect to x of this natural, about to write an h, ln function of x, there we go, that should be an ln, apologies. When we take the derivative of the natural log of x, its derivative is going to be 1 over x, or x to the negative 1, if you want to think of it that way. That is going to be the derivative. So you may look at this and think, okay, well this looks like something that maybe I got from the power rule, right? Maybe I could get something like this from the power rule. Well, remember how the power rule works. The power rule says that if we have something like x to the n power and we take the derivative, we bring down the exponent and then we decrease the exponent by 1. Well, how would you get to an exponent of negative 1 using the power rule? Well, in order to get to an exponent of negative 1, you would have had to have started with an exponent of 0 in order to subtract and get to a negative 1. Well, anything with an exponent of 0 is really just a constant though. And we know if we take the derivative of a constant, it just goes away, it just goes to 0. It doesn't generate anything like this. So this truly is a completely different rule than what might result from the power rule, where it looks like maybe we get something similar. It doesn't actually work that way because the only way we could get the power rule to generate something like this would require us using something where the power rule doesn't actually apply. So anytime we take the derivative of the natural log function, it evaluates to 1 over x. So let's try a few examples using just the basic rule and then adding in some of the other rules that we've used in the past. So suppose our function is y is equal to 3 times the natural log of x. We want to differentiate this function. So the derivative of y with respect to x, we have a coefficient in front of our function. Okay, we know the coefficient doesn't affect the derivative, we just multiply it by the derivative. So we're just differentiating the natural log of x, and we know its derivative is going to be 1 over x. So our derivative is going to be 3 times 1 over x. And if we simplify that down, how's this going to work? Well, remember 3, think of that as 3 over 1. So our numerators multiply straight across, as do our denominators. So that simplifies to 3 over x. Okay, next one. Y is equal to x squared times the natural log of x. So I see a product right there, plus 5x. So what is the derivative of this function with respect to x? So for the first term, again, this represents a product, so think of x squared as one function, think of natural log of x as one function. We have to use the product rule here. So the product rule says to differentiate that particular portion of this function, it's going to be the first part times the derivative of the second. Well, the derivative of natural log of x is going to be 1 over x, plus the second part, so natural log of x, times the derivative of the first, which is going to be 2x. So this is going to be the derivative resulting from the product rule applied to our first term. Don't forget we have another term over here though, so we can just take its derivative by itself. So the derivative of 5x is just going to be 5, so plus 5. So let's clean all of that up. So x squared times 1 over x, again think of this over 1 if it helps. That means we have an x squared in the numerator and an x in the denominator. So that means one of those x's reduces and we're just left with a single x. Now for the next term, kind of like with exponentials, we have a specific hierarchy in terms of the order we write things in. So here's something that's really tempting to do that you cannot do. This x and this x do not multiply together. Remember, this x is inside of the logarithmic function. It's kind of like being under a square root. Remember, nothing goes in. Something under the square root does not combine with something that's not under a square root. The same rule applies to something that is inside of a logarithm. So this particular term is just the natural log of x, which is 1 unit, times 2 times x. All of those individual factors multiplied together. Now, just with an exponential, typically we write whatever our coefficient is first, then whatever would be considered polynomial, in other words our x, and then we would write the exponential or the logarithm in this case. So all of that is multiplied by the natural log of x. And notice by writing it in this order, it's a little clearer that the x and then the x inside the natural log are not actually going to combine together. And so then we have that additional 5. Now if we had a greatest common factor, we could potentially factor it out, but in this case, none of these terms has anything in common, so we can just leave that as is. Okay, let's look at another example. So that particular one uses the product rule. What about the quotient rule? What if we have a natural log involved in a function where the quotient rule applies? So we have the natural log of x on top, we have x cubed on the bottom. So our derivative rule says low, so x cubed, d high, well the derivative of our natural log function is going to be 1 over x, minus high, so natural log of x, d low, so 3x squared, all over the lower function squared. So x cubed squared. So let's clean that up. Now for our first term, right now we have a fraction inside of a fraction, but notice what's going to happen here. Essentially what happens here is the same thing as what happened here. X cubed is the same thing as x cubed over 1, which means we have an x cubed in the numerator and an x in the denominator. So we have one x in common on top and bottom. That x cancels, leaving us with just an x squared from that term. Minus, rearrange everything, write it in 3x squared times ln x order, and then all of that is divided by x cubed squared, which will be x to the 6th power. Now, because we're looking at something where we have both a numerator and a denominator, there's the possibility that we may have a common factor that reduces. So notice in the numerator we have a factor of x squared in common among those two terms. So we're going to factor that out. So factor out the x squared, which is going to leave us with nothing from the first term. Nothing does not mean 0 here though, it means 1. Factoring is the same thing as division. So if you divide something out from itself, division of anything by itself leaves a 1. And then from the next term, we have 3 ln x. And all of that is divided by x to the 6th power. So we have a factor of x squared in the numerator that can cancel with an x squared in the denominator, which leaves us with 4 x's in the denominator. So in the denominator, we have x to the 4th power. Now remember, nothing cancels with this x. This x is inside of the logarithm function. ln of x is 1 unit. Nothing reduces with that except maybe another ln of x. Okay, So now let's talk about what would happen if we need to use the chain rule in conjunction with the natural log. So when would something like this apply? This would apply when we have something of the form natural log with another function as its input. So as with any chain rule situation, we take the derivative of the outer function, leaving the inner function alone, and then we take that entire expression and multiply by the derivative of the inner function. So here our outer function, we're taking the derivative with respect to x of natural log of f of x. So the derivative of our outer function, well, the outer function is the natural log function. And we know if we take the derivative of the natural log function, it's just going to be 1 over x. X was the input for the natural log. Well, now the input is not necessarily just x, it's maybe something else involving x, but the structure is the same. So the derivative of the outside function is going to be 1 over whatever's inside the natural log. So in this case, that's going to be 1 over f of x. And then we're going to multiply by the derivative of the inner function. So times f prime of x. And then a simpler way to write this, if we want, would be f prime of x divided by f of x. I tend to just think of it in terms like this so that it's clear where one portion and the other portion of our derivative come from, but this would be the simpler version of what happens when we apply the chain rule to our natural logarithm. So let's look at a few examples where we need to use the chain rule. Okay, what about natural log of 3x? So now we have our natural log function, but we don't just have an x inside, we have an additional function that involves x. So start with the outer function, in this case our natural log. So we're going to take the derivative of the natural log, which says 1 over whatever the input for the natural log is. So in this case 1 over 3x. So 1 over 3x times the derivative of the inner function. Well, the derivative of 3x is going to be 3. So when we combine those two together, 3 is going to go to the numerator. So that's going to be 3 over 3x. And in this case, we have that common factor of 3 that reduces, and we're just left with 1 over x. So interestingly enough, even though this function technically required the chain rule to differentiate, when we took its derivative, we still ended up with the basic derivative for natural log. Occasionally something like that is going to happen. Okay, that will not happen in this case because we have something a little bit more complicated inside this natural log. So what's our derivative here? We'll again start with the outer function. So the derivative of the natural log is going to be 1 over whatever's inside the natural log. So 1 over x squared minus 5. And then we're going to multiply by the derivative of the inner function, which is going to be 2x. And now 2x can go to the numerator. So that's going to be 2x divided by x squared minus 5. Okay, let's look at one last example before we look at an application problem. Now we're going to approach this one from a couple of different ways. Keep in mind, we still have all of those logarithm rules that we looked at earlier in the section. And in some cases, when we're trying to differentiate something that involves a logarithm, where one of those rules may or may not apply, sometimes using a logarithm rule first will make the differentiation simpler. It's not necessarily required. We can still get down to the same answer, but sometimes it may make the problem a little bit easier. It may make some of the intermediate algebra a little bit easier. Regardless, it just provides a slightly different approach to taking the derivative. So let's start by just applying your standard differentiation technique, noting that what's inside the logarithm is a quotient, So using the chain rule and then differentiating the inner function requires both the chain rule and the quotient rule. So for the first approach, let's just use the quotient rule like we normally would. And then for our second approach, we're going to see if we can simplify this, rewrite this using a logarithm rule first. So just quotient rule first. So we're taking the derivative of y with respect to x. So we're differentiating the outer function, the natural log function. So the rule says it's going to be 1 over whatever is inside. So in this case, that's going to be a fraction inside of a fraction. So 1 over whatever happens to be inside the logarithm. So there's that. Then we're going to multiply by the derivative of the inner function. Now the inner function is a quotient, so taking the derivative of the inner function requires use of the quotient rule, So we take the quotient rule, so low d high, which is going to be 3x squared, minus high d low, all over low squared. So whatever that simplifies down to, that is our derivative. So let's take care of this first. So 1 over a fraction, 1 divided by a fraction. Well, remember, dividing by a fraction is the same thing as multiplying by that fraction's reciprocal. So 1 divided by all of this is the same thing as 1 multiplied by the reciprocal. So all of this really just simplifies down to the reciprocal of the denominator. So that's going to be x divided by x cubed plus 4. Okay, now let's look at the rest of it. So multiplied by that, we have all of this. So 3x squared times x, that's going to be 3x cubed. And then multiplied by 1 and multiplied by a negative 1, we have negative x cubed, and then negative 4. And then all of that is divided by x squared. So keep going. We can distribute the x in the numerator. First off, I would go ahead and combine these two terms though. What are those going to combine to? So we have 3x cubed minus x cubed, so 2x cubed in total minus 4. And then we can distribute that x. So that's going to be 2x to the 4th, and then x times negative 4 is going to be negative 4x. All of that over x squared times x cubed plus 4. Okay, so I'm noticing now I went ahead and distributed that x, but that may or may not have been beneficial. Because notice what now happens. We have a factor of x squared in the denominator, and we have an x in common in the numerator. So for better or worse, I'm going to backtrack. I'm going to factor that x out again. So we have 2x now cubed minus 4. I could factor out the 2 as well if I want, but that's not going to help me with the goal at the moment, which is to reduce anything that's common in the numerator and denominator. So the benefit here is now we have that common factor of x that reduces with the x squared in the denominator. So we're just left with 2x cubed minus 4 in the numerator. One of those x's reduces, so we're just left with a single x, and then x cubed plus 4 in the denominator. So that is going to be our derivative. Notice nothing else is going to cancel. It almost looks like maybe we could do something here, but because we can't cancel the whole factor, that's about all we can do. We could distribute the x in the denominator if we want, or we can just leave it as is. So that's one approach to using the chain rule and then the quotient rule to take this derivative. The drawback maybe to using that strategy is notice you end up with a fraction inside of a fraction, which may or may not be daunting to see. The rest of the simplification is fairly straightforward, But I just want to look at another approach we could take that wouldn't require us to use the quotient rule. So when I look at this particular logarithm, I notice it's a logarithm of a quotient, which is hence the quotient rule, why we ended up using the quotient rule. Well, we know there's a rule for logarithms that says if we're applying a logarithm to a quotient, we can split it up into the logarithm of the numerator and the denominator and then subtract them. So another way to write the function we're differentiating is as the natural log of x cubed plus 4 minus the natural log of x. That's another way of writing this particular function. And the benefit here is if we now differentiate in this form, we no longer have to use something like the quotient rule. We'll need the chain rule right here, but for this second natural log, we can just take the derivative using that standard natural log rule. So now let's differentiate using this version of the function. And we will get to the same answer, it's just going to look slightly different in the middle of the problem. So for our first term, natural log of x cubed plus 4, so the differential rule says it's going to be 1 over whatever's inside the logarithm. So 1 over x cubed plus 4 times the derivative of the inner function, so times 3x squared. Okay, and then for the second term, it's just a plain old natural log. So minus the derivative of this, which is just going to be 1 over x. And notice that's quite a bit simpler than what we have right here that we then had to simplify after using the quotient rule. So for this first term, the 3x squared goes into the numerator. So 3x squared over x cubed plus 4. And then we're subtracting 1 over x. Now in general, we like to combine rational expressions together. So in this case, we want to combine these two fractions. We need a common denominator. So for our first expression, we're going to need to multiply by x on top and bottom. So that's going to give us a 3x cubed when we multiply by x on top and bottom. I'll write it in. So times x times x. We'll worry about the denominator in just a minute. And then over here for this one, we're missing the x cubed plus 4. So times x cubed plus 4, and then times x cubed plus 4. So we're subtracting 1 times x cubed plus 4. And then in our denominator, we just have the x times x cubed plus 4. And notice that was our denominator for our previous problem, so I'm just going to leave it in that form. So last but not least, let's just distribute that negative, combine our like terms. So we have 3x cubed minus x cubed, so that's going to leave us with 2x cubed. And then the subtraction also has to distribute to the 4, so minus 4. And then our denominator is going to be x times x cubed plus 4. So notice exact same expression, just slightly different work in the middle. So here the most complicated thing we had to do was get that common denominator, but ultimately we have the same answer. I would argue that maybe taking this approach is a little simpler. It avoids the fraction inside of the fraction and it avoids this slightly more complicated expression, but either approach is perfectly fine. It's really just personal preference at that point. So let's look at an application problem. Again, just as e to the x pops up in real life, so does the natural log, because they are so closely related. Okay, so the profit in thousands of dollars from the sale of x thousand units of the product, so pay attention to these units. So output is thousands of dollars, input is thousands of units sold. That can be estimated by the following function. P of x is equal to 2 times x minus 0.3x times the natural log of x. So the first thing we want to do is find the marginal profit P prime of x. So not a specific value at a specific value of x, but essentially the formula for marginal profit, otherwise known as the derivative. So p prime of x, we're going to take the derivative of this function. Now the first term, we can just use the power rule, so that's just going to be 2. Now for the second term, it's going to be a product rule. So I'm going to go ahead and put the subtraction, and then we're going to subtract the whole derivative. So I'm going to think of 0.3x as the first function and natural log of x as the second function. So the product rule says first function, so 0.3x, times the derivative of the second function, so 1 over x, plus the second function, so natural log of x, times the derivative of the first function, which is just going to be 0.3. Okay, and there's our derivative. So let's clean that up. So we have 2. Notice the subtraction sign will distribute to both terms, so both of those are going to be negative. Now what happens with this first term? So we have 0.3x. We can put that over 1 if it helps. That tells us we have an x in the numerator and an x in the denominator. So those x's reduce to 1, just leaving us with the 0.3. So minus 0.3. And then for this next term, remember the subtraction distributes, and then it's just a 0.3, that's the coefficient for natural log of x. So minus 0.3 times the natural log of x. So notice now we have two constants that can combine. This 0.3 is now a coefficient, so this is not a like term with these two. So 2 minus 0.3 is going to give us 1.7. So 1.7 minus 0.3 times the natural log of x. Okay, next we want to find p prime of 150 and explain what this number represents. Well, we have p prime, we have the derivative. We want to evaluate this at an input of 150. So p prime of 150 is equal to 1.7 minus 0.3 times the natural log of 150. Okay. So if we want an exact value, that's what we leave. We leave it as that. It's going to be more meaningful in this situation to have an approximation. And since we are talking about dollar amounts, we go accordingly. So let's plug this in. So 1.7 minus 0.3 times the natural log of 150. Okay, so your calculator again knows you multiply before you subtract, so it will evaluate this the way you've written it. And there we go. So 0.196. Let's keep as many decimal places as we can at this moment. So 0.196, and we'll say 81. Okay, now what does this mean? Let's go back to the units. So we were told that inputs represent thousands of units. So this was 150,000 units. So 150 means really 150,000 units. And we were also told that profit, the output, is in thousands of dollars. So this is a thousands of dollars. This is a value of thousands of dollars. So if we want to know what this really means, this is thousands of dollars. So we'd multiply it by 1,000. So that really means, if we're talking about a dollar amount, we've converted it to thousands, that really means $196.81. So what does this really mean? Well, it means when P is 150, our profit is increasing by this amount. So this is the increase in profit when X equals 150. Remember, marginal profit means the additional profit that we gain when we increase by 1, when we increase our variable by 1. So this is going to be the increase in profit at that moment in time when we're producing 150, in this case 150,000 units. So our last question is, how many thousands of units should be sold to maximize profit? And we want to round to the nearest hundredth as needed. Okay. Well, we know what this means, right? We know how to maximize. Again, we use the derivative. Let's go back to what we know about maximization. So we know that maximization, minimization, those values always occur wherever our derivative is either undefined or wherever our derivative is equal to 0. So remember, we're looking for critical values, those x values where we see one or the other of those situations. Either the derivative evaluates to 0 or the derivative is undefined. And then based on what we see around those critical values, that tells us whether or not we have a maximum or a minimum. So we want to let our derivative be equal to 0 to find our critical values. That means 1.7 minus 0.3 times the natural log of x is equal to 0. So now we need to isolate x, which for now just means isolating the natural log of x. So we'll start by subtracting the 1.7. Now watch your signs, because that's now going to leave you with a negative 0.3 coefficient on your natural log. And that's going to be equal to negative 1.7. And so if we divide out our coefficient, we get natural log of x is equal to negative 1.7 divided by negative 0.3, and we get a long number. So just do your best, just approximate. Keep as many decimal places as you can. If we're going to round to the nearest hundredth, 2 places at the end. Typically keep maybe 4 or 5 while you're working. And so there we go. So we're looking for the value of x that would make this true. Now if you think back to what we did near the beginning of this section, I'm going to flip back over to the first page. Essentially what we're looking at right here is the same as what we looked at right here, this particular equation. So we had a logarithm applied to an unknown input, and we knew what the logarithm would evaluate to. So we have a logarithm of base e, in this case, applied to an unknown input, and it evaluates to this particular amount. So in order to determine what the actual unknown amount is, remember we converted this to an exponential equation, to something that's corresponding in exponential form. So the base of the logarithm becomes the base of the exponential, and then the other values switch places. That applies here as well. Now what is the base of this logarithm though? If we're talking about ln, remember that means log base e. So if we want to convert this statement to something exponential, it's going to convert to an exponential with a base of e. So that's going to convert, and then the other two values, remember they switch places around the equal sign. So that means this is now going to be the exponent. So 5.66667, the number we have in the calculator right now, and that is going to be equal to x. So that represents x. So e to that power is our value that we want. So there's our e, second and natural log. Now rather than typing in 5.66667, I'm just going to copy the previous line using the answer button. So right above negative in blue it says a and s. So second and negative brings in the answer from the previous line. And that way I don't have to round anything. And so there we go. So to the nearest hundredth, that's going to be approximately 289.07. Well, what does that mean? What does this represent? We're talking about an applied problem. Well, the question is, how many thousands of units should be sold to maximize profit? X is in thousands of units. So this is thousands thousands of units. So the only thing left to verify is that this does in fact represent the location of a maximum. This does in fact represent a maximum value for profit and not just a random value or somehow a minimum value. So this is where we check our derivative's sign on either side of this particular critical value. So this is the critical value, the one critical value for this function. We want to know what's happening to the left of that critical value, what's happening to the right. So pick a value less than 289.07, pick a value larger. They can be a lot smaller, it can be a lot larger, it doesn't matter. So I'm going to pick 288, something close but smaller, and then I'm going to pick 290 for when I'm above that. So I want to check the sign of the derivative evaluated at each of these individual values. So remember, here's our derivative, there's the expression for our derivative. I want to evaluate this for 288, and I want to evaluate it for 290. So let's start with 288. So 1.7 minus 0.3 times the natural log of 288. And there we go. So when we evaluate that, I'm not super interested in what the exact number is. What I care about is the fact that it's a positive number. So if the derivative evaluates here to a positive number, that means my function is increasing over that interval. So for all values of x less than 289 for which this function is defined, our function is increasing. Now what happens when we cross over the critical value and get to 290? So 1.7 minus 0.3 times the natural log of 290. Well, now we go to a negative value. So that E means scientific notation. So essentially that means take the decimal that you see listed and move it 4 places to the left and then just fill in zeros where you have holes. But again, more importantly is the fact that this is negative. So that means the function is decreasing over the next interval. So if our graph goes from increasing to decreasing, that means we peaked at the top and then we're decreasing from there. So that does, in fact, represent the location for a maximum. So this is going to be the production level that gives us the maximum amount of profit. So these past 2 videos have given us options for differentiating a whole new set of functions. So exponential functions are different from functions for which you'd apply the product rule, or not the product rule, excuse me, the power rule. The power rule is only going to apply when our base is variable and then when our exponent is a fixed number. So if we flip that so that the base is a fixed number and the exponent is variable, we have to use the rule for exponential functions. If we can differentiate an exponential function, we can also differentiate a logarithmic function, and so this opens up a bunch of additional possibilities for us.